Okay, good afternoon everybody. Welcome to this new edition of the IPARCOS colloquia. Before we start, I should announce that the next colloquium will be by Andreu Font, and it will be about the expanding universe, and in particular studying it from the point of view of the results obtained by the dark energy spectroscopic instrument. And this will happen the 15th of November. Okay, so everybody is welcome to this colloquium about cosmology that will take place in a month's time. And now I think that the best thing that I can do is let Ignacio Sinemi, which is the head of the Institute IPARCOS, to present our speaker, Iain Stewart.
So thanks a lot, Luis. It is a pleasure to introduce Iain Stewart from Massachusetts Institute of Technology. Iain Stewart is one of the world's most famous experts in quantum chromodynamics. He has developed something which is called an effective field theory, called a soft collinear effective theory. And he has analyzed a lot of processes. I cannot even imagine how many papers or processes you did. And he has come here on occasion of a congress that we are running these days. So he asked if he kindly could give a talk for the general public. And so this fit perfectly in the talk of IPARCOS. And this is also to introduce a student to what are the research lines in this field in these days. And I think that nobody better than him can explain us and tell us about that. So please, Iain.
Thanks a lot. So I want to tell you today about 50 years of QCD. So it turns out that this year we are celebrating a 50-year anniversary of this field of strong interactions. It was kind of born roughly 50 years ago, and so that's an opportune time to talk about what's happened in that past 50 years, and that's what I plan to do in this colloquium. So let me just start out more broadly, thinking about kind of all of physics, trying to put it in a one-dimensional plot. So physics can be thought of as a study of different distance scales, everything from astrophysics at very large scales down to quantum gravity at very small scales, and then we're in the middle somewhere. Today's talk is going to be about physics of the Standard Model, which kind of covers this middle period. It's not all of physics, it's part of physics. There's things that aren't fitting in the Standard Model, like dark matter, that are also very interesting, and we don't really know where dark matter lies here. And there's also sort of physics beyond the Standard Model, perhaps, but that's not the topic of today's talk. So today's talk... Yeah, it's just slow. Today's talk is going to focus on the Standard Model, in particular one part of the Standard Model. So what is the Standard Model? Standard Model is gravity. Electromagnetism, strong, or at least part of gravity, electromagnetism, which we're all familiar with, the strong force which binds together quarks and gluons inside of the proton, and I'll be focusing on that today. And the weak force, which causes radioactive decay, is also part of the Standard Model. It'll show up from time to time during my talk, but our focus will be here on the strong force. We seem to have a bit of a delay on the remote, which will cause me to go slower. So here's the outline for my talk. We'll have three different parts. An introduction, and then sort of the bulk of the talk will be talking about what's happened in the past 50 years in the strong force field, and then I'm going to end the talk with giving you some interesting tidbits of unsolved problems in this field that we hope to solve in the next 50 years. Some of them are pretty tough problems, and they may even take more than 50 years. So that's the outline. So let's start out with just what is this strong interaction that I've been talking about. So the strong interaction describes quarks and gluons. In the Standard Model, there's 6 different quarks: up, charm, top, down, strange, bottom. So they have particular names. It's kind of fun. As well as the gluon. And these are the particles that appear inside a proton that bind the proton together the constituents of a proton. The fact that the force is strong makes some calculations difficult in ways that I will describe. It also makes the phenomenology of this force really rich, and I will give you an overview of all the very interesting phenomena that arise just from this strong force. It's also crucial when we want to look for physics that's maybe beyond the Standard Model. If we want to probe what does nature look like at very short distances, then we often do that by colliding very energetic particles together. And the strong force is responsible in describing those types of collisions and trying to probe at what's happening at very short distances by looking at very high energies. It's responsible sort of for the hardest part of the problem, and I'll describe some of that in my talk today. So it plays a role in a lot of experimental facilities, both the PASS collider, which was a lepton collider, electron positron in the CERN ring here. Low energy colliders that collide electrons and protons, such as this collider at Jefferson Lab in the US, as well as the Large Hadron Collider at CERN, which is a proton-proton collider. So as I said, QCD is a very rich theory. It's actually described by a remarkably simple formula. I won't go too deep into the formula, but here is a formula. That's the definition of the QCD Lagrangian. And out of that Lagrangian comes a remarkable set of states, remarkable states of matter, a remarkable range of phenomena, and it's led to a development of different fields of physics. So from this one theory, we have different fields that have separate meetings. We're having one of those separate meetings here in Madrid this week called the REF conference. But hundreds of physicists each participating in sort of subfields of this strong interaction framework. So let me start with the states of matter that's in color-coded magenta on this slide. So we have the hadrons. I already mentioned a hadron to you, the proton. But what is the proton? The proton is a bag of quarks and gluons, but it's a relativistic bound state. So the particles are zipping around inside this proton, moving very, very fast, but somehow they're still bound in this bag that constitutes the proton at some finite distance. And that's because of the nature of the strong force. And there's also, it's a quantum mechanical system, so there's quantum fluctuations. It's not just like three constituent quarks rattling around inside a sphere. It's much more complicated. Out of the vacuum pop pairs of particles, and then they disappear again. So it's a very, very complicated system, and we've been studying it pretty much for the entire 50 years of the history of this topic. But it's not just, the topic doesn't just end with sort of studying a proton. Out of a proton and its cousin, the neutron, we can build nuclei and talk about atomic levels with different atoms. And we can also instead take neutrons and build a neutron star. So these are different states of matter that come from QCD. If we try to liberate the quarks and gluons by really heating up the system, go to very high temperature, that's something that happened in the early universe, and we can also try to reproduce that in what's called a heavy ion collision, then we can hope to form another state of matter, and we believe we have formed it, called the quark-gluon plasma, where we have liberated quarks and gluons with some collective flow. There's other phenomena that are kind of emergent phenomena of QCD that I'll talk about in my talk called jets. And so there's lots of different things that come out of this one simple theory. So that's an example of the states. What about the phenomena? So I won't go through all the phenomena here. There's a really important one called asymptotic freedom. I'll talk about some of these in the subsequent slides. But there's a lot of different rich phenomena that come out of this single theory that you would never have guessed by just looking at the simple formula. And we'll talk about some of these things throughout the talk. So in some sense, this is kind of an outline. And there's also, as I said, a bunch of different fields, and just listed on the side here what type of fields they are. So there's a study of these colliders. That's a very important part of QCD. There's a study of kind of the formal aspects of this theory. That's this factorization. There's study of various phenomena that led to fields of their own, et cetera. And we'll talk about some of these fields throughout the talk. Okay, so let me tell you a little bit more detail what QCD is. So QCD is governed by a coupling. This is how strongly do things interact, and the coupling is large for a range of phenomena. rather than talking about a coupling G, we often square it because it likes to come in squared. So we talk about a coupling alpha, which is the coupling squared divided by 4 pi. And that tells us about how strong the quarks interact with gluons. Because this is what's called a non-abelian group, it turns out that the gluons, the force carriers, interact with themselves through these types of interactions between 3 of them and 4 of them. And this is what the Lagrangian that I wrote down for you describes, how these things interact. They all interact with this same strength, alpha. Almost all the systems that we're interested in have relativity playing an important role. And the coupling, as I mentioned, is strong, and it's often large, so we can't really do a coupling expansion like we do in quantum electrodynamics. If you take a course in non-relativistic quantum mechanics and you think about the hydrogen atom, you expand in alpha, and you make a lot of headway that way, and we can't really do that for a lot of problems here, so we have to be more inventive. This theory is called the quantum chromodynamics because there's color. Chromo refers to color. And the charge that things carry, the analog of electromagnetic charge, plus and minus, it's more complicated here. We have 3 different colors of quarks, red, blue, and green. And the gluons also have colors. They come in 8 different varieties. And so we can kind of signify color flow in a diagram like this one, where the quark is blue and it exchanges the gluon and then becomes a red quark. So this is kind of give you a picture for how color might flow around in some interactions. So we won't stare too much at these formulas, but they just describe that. And out of this Lagrangian, as I said, comes the proton that I talked about, comes the plasma that I talked about, and comes these jets. And these are not things that are apparent from the Lagrangian itself. If I stare at that Lagrangian, I don't see these phenomena. I have to do something. I have to do some calculations in order to see those emergent phenomena. So it's kind of like condensed matter in a way, where we have a simple system, but there's some other phenomena that show up, and maybe those will be important to describe them even as degrees of freedom instead of the sort of fundamental ones, and we'll see examples of that in the talk. Now, I said that the coupling is strong, and that is absolutely the case for why the quarks and gluons are bound inside this proton, but the coupling is also weak. And that's because it depends on the energy resolution. This parameter mu is an energy scale, and depending on what energy scale the interactions take place at, the value of the coupling changes. And that's what this picture shows. It's a function, the coupling is a function of the energy scale in gigaelectrovolts, or basically units of the proton mass. And so if we're at the unit, around the proton mass, it's very strong, but if we go to 1,000 times the proton mass, it becomes very weak. And the phenomena that we talked about called jets shows up at the weak coupling, whereas the binding of the proton shows up at strong coupling. And this is the famous, this plot and this change in the coupling is due to asymptotic freedom, namely that there's a slope to the coupling. And I can calculate something called a beta function, which is just the derivative of the coupling, what is the slope. And the fact that that coupling was getting smaller as I increased the energy scale means that the slope is negative. It was falling off, right? And so the famous calculation of Gross, Wilczek, and Pulitzer, which won them a Nobel Prize and led to this concept of asymptotic freedom, is the fact that this is a negative number. So it's a calculable quantity, and it's a negative number for the standard model. So QCD gets weaker at large energy, and in fact, as you go to very, very large energy, the quarks essentially become free, which is kind of remarkable. The higher and higher energy we might probe a system, the more and more the quarks and gluons inside of it look like free particles that don't interact with each other. But on the other hand, at low energy, the coupling grows. That's kind of the opposite statement. And that's what lets the coupling become strong and enables it to form these bound states, these hadrons, like the proton. Okay, so we have the kind of combination of these two phenomena in this plot. We have sort of what's called confinement down here and asymptotic freedom up here. There's also only a single scale in this theory. It's sort of an emergent scale. It's related to the scale of the coupling. You can think of it as the scale in this plot, which is actually at a finite value, where this thing blows up. At some finite value of the resolution, the coupling goes to infinity. That defines a scale. And that scale, the mass of the proton is actually proportional to the scale. The size of the proton is inversely proportional to the scale. So you can do a lot of dimensional analysis just with this one number, which is of order 300 MeV. Now, because quarks and gluons are bound inside hadrons, we actually never see them freely. So we infer their existence experimentally because we have this theory of quarks and gluons, and it makes certain predictions, but we don't actually pick one out in the laboratory and actually see it with our naked eye. Instead, we see the hadrons, the bound states of the quarks and gluons, like the proton. So you might say, well, at very high energies, can't you just like pound on a proton and liberate one of these quarks off into space? And yeah, you can. You can knock a quark out of the proton. But what's going to happen to that quark is it's going to find some friends and become another proton. And that's because the force is so strong that this is an inevitable thing, and it just doesn't want to exist on its own. So this year, about a month ago, a little over a month ago, we celebrated 50 years of QCD with a conference at UCLA called 50 Years of QCD. And we had a variety of talks about all aspects of QCD over the course of a week. And what I'm going to try to do in this colloquium is sort of put what was talked about at that conference on a kind of time frame and give you some snapshots of some of the things that happened in the field over the past 50 years. There's also been a book that a number of us worked on and to summarize ideas of what's happened in the past 50 years. All right, so here's the timeline. Asymptotic freedom, that was 50 years ago, 1973. We're in 2023, so 50 years in the future. So let me start with the early period. So, and I'll talk about like sort of, it's a little messy here, but a lot of things were happening at that time. There's a lot of confusion around the physics of hadrons at that time until QCD emerged. And I'll kind of step you through this. I should also mention that I said there was a Nobel Prize for asymptotic freedom, but it wasn't the only Nobel Prize. There was also experimental Nobel Prizes, both for what's called Bjorken scaling, which we'll describe in a minute, and the discovery of the charm quark, which were kind of central in the story as well. So let's start with Bjorken scaling. This is pre-QCD, and people were studying what happens when I scatter electrons on protons at higher and higher energy, and something called deep inelastic scattering, where I break the proton apart, and I actually see inside the proton, and I learned that something remarkable happens. It kind of looks like I'm scattering off point-like particles. And that's how we sort of got a notion originally. People didn't know they were quarks. Feynman called them partons. And Bjorken made a prediction, what's called scaling, that things would be independent of how energetic the electron I send in is, essentially. If I probe the system at different energy scales or different resolution scales, it would look the same. And there's some messy data here, but you're just supposed to see that the data, which has different resolution scales, is all kind of lying around the same curve, and that's the original plot for the showing scaling in deep inelastic scattering. This is a plot from 1968. It was a plot in a summary talk that wasn't actually shown in the conference, but only in the summary. Okay, before this calculation of asymptotic freedom, there was also an important advance where the sort of degrees of freedom, the quarks and how they're charged, was worked out in this paper by Fritsch and company. And that was based on sort of hadron spectroscopy. What do I need? What kind of quantum numbers does the system need to have in order to satisfy Fermi statistics? And taken seriously, that also led to the proposal that there'd be a vector gluon that would couple to the quarks, and that the gauge group would be what's called SU3, so special unitary rotations, so unitary 3x3 matrices that are determinant 1. It's a group. And then there's the discovery of asymptotic freedom, and really that allowed the theory to come on a firm footing, because we had observed these hadrons, and we'd observed this scaling, but we had no idea that a single theory could describe both of those phenomena. So the partons became the quarks and gluons, and we could describe the hadrons at the same time because of this picture that I showed you of how the coupling changes. Now, people needed to understand the theory, and one way that they did that is they took the number of colors, which was 3, as I told you, and they said, well, we could expand in that. Well, we can't expand in 3, but we could expand in 1/3, And it turned out that there was like qualitative things that we could learn about the theory, and this was work due to 't Hooft, just from doing that type of expansion. In particular, you could show that this property that I called confinement, where the particles are confined inside a hadron, that property you could demonstrate happens in a lower number of dimensions in a theory like QCD. So people started to learn qualitative things about QCD in this way. I'm from MIT, so I should mention what's called the MIT bag model. This was a sort of famous model that people came up with, which wasn't QCD itself, but tried to package the properties of QCD into a predictive framework. And my colleagues, or former colleagues at MIT, came up with this bag model that's still in use sometimes today when people want to model things. Now, also at that time, a method that sort of directly deals with the theory as given without making those type of approximations that you would have in a model was also invented, and that's known as lattice QCD. So what we do is we try to discretize the theory, so there's some discretization of the theory, and we solve the theory on a computer. Now, a rather big computer, because the number of degrees we're simulating is like 10 to the 9, and so we're doing some integral over a lot of space. We're using Monte Carlo techniques to do that, and we're doing importance sampling to try to simulate what's basically called a path integral, or so you can think of the path integral formulation of quantum mechanics. We're doing a path integral formulation of QCD here, and we're simulating observables that can be put into this formalism on a computer. And that's been a very fruitful thing. It took a long time to make this, this was proposed very early on, but it took a long time for it to become very rigorous, and I'll talk a little bit about some of those calculations today. Now, the confinement mechanism, though not in detail, but the basic ideas were also worked out around this time, and the basic idea is that there's a flux tube, electric flux tube, that forms if you try to separate two of these charged particles, and that flux tube is pulling back on the particles when you go to larger distances in a way that ends up with giving you a linear potential. So you have a potential that falls off like 1 over r, and then it becomes linear, so that the particles don't want to be pulled apart. They want to come back with a linear attraction. And what happens eventually, though, is that this kind of string that forms between the quarks breaks, and you get another pair of particles, another pair of particles. So there's kind of it's a quantum mechanical system, so when you're pulling apart, you might induce so much energy in between that another pair of particles can pop out of the vacuum, and you get multiple strings. So a lot of these things were understood pretty early on in the history. Then in the next period, which I put around 1980, again, there's sort of individual accomplishments here on this chart, and I'll describe to you sort of a lot of them. I've put the authors here in brown color. I'll describe a lot of them kind of together rather than sort of going one by one through them. There's this appearance of these sprays of radiation that I referred to as jets, and then that came about from trying to understand what's a reasonable observable in this theory of QCD. How do I think about even making measurements? What am I allowed to talk about measuring? And that led to this concept of jets, which was originally something that people were puzzled over, and even the paper that proposed these jets took a lot of effort actually to even get published. Now it's something we just take for granted, and we often even don't cite it. It's so popular. Okay, so there was a lot of developments here, including also eventually this experimental discovery of gluons by Petro experiment. And let me talk about some of these in a series of things. So let me tell you what a high energy collision looks like. So let's say we have two protons. I'm going to describe it from the point of view of the Large Hadron Collider, and we'll just play a little movie and see what those collisions look like. So here's quarks rattling around inside a proton, artist conception, and there's a big collider here. We collide two of the partons inside the proton. Maybe we produce a Higgs boson. And that Higgs boson lives for a very short time, not this amount of time, very, very short, before it decays. And then it goes out and spreads out into patterns of radiation, maybe some leptons as well as some quarks. The quarks form these jets, sprays of radiation that you can kind of see here. So that's an artist's conception of what one of these collisions look like. And then those sprays of radiation leave energy deposits in our detector, and that's how we sort of get a picture of what's going on in the collision. So that was just a movie, but here's sort of a real event. from the Alice experiment, showing these sprays of radiation, showing also some forward radiation that happens when this collision happens, and these here are indications of these jets that I mentioned to you, sprays of radiation in the final state, indicating that at short distances there was a pair of these quarks produced, for example. So here's a jet, here's another jet. So this is the type of thing that you can get access to, and it's the type of thing that QCD predicts. And so let me tell you a little bit about how QCD predicts it and some of the things on that timeline. So we have these protons. Here I'm now drawing a cartoon. I have these protons, and I collide them. And actually what I collide are, say, two of the particles inside the proton. Something happens, and I get these jets, and maybe I get a pair of leptons. So you could say, if you looked in, zoomed in on this very short distance and asked what happened, well, maybe what happened is I took two gluons from those protons, and they actually collide. The Higgs boson likes to be produced by gluons. So let's say that happened. And then the Higgs boson doesn't live for very long, and it quickly decayed. In the movie, it decayed to two Z bosons. So let's say it decayed to two Z bosons. The Z bosons also don't live very long. They decayed to some quarks. And then those quarks are what is forming these jets. So individually, you start off with this quark. It was produced not inside a bag like the proton, but by itself. And then it formed a jet. And so what happens is that QCD likes to preferably to produce radiation along the path of the motion of a particle. So if I have a very energetic quark traveling in some direction, it's going to split and keep splitting, but along the direction that it's traveling. And that's governed in my chart by what's called the DGLOP equation, and that's giving you a definite equation for how things like to split in this collimated way or collinear way. And because of that, the particles, which individually started out as a single particle, form these jets. Eventually, this hadronization process happens, and then I get hadrons in the final, at the end of the day. So that's what these little circles are in my picture. So that's, and then that's what you actually detect. There's also sort of soft radiation, so softer hadrons that couple to the lines in this diagram. And that describes to you sort of these DGLOP equations, which are describing this splitting process. It describes to you a little bit, it doesn't yet describe to you this factorization. I'll come to that in a minute. How do the particles in this spray of radiation form into hadrons? People built models for that, and two very important ones in the history of models that describe hadronization were the Feynman field and Lund model. I haven't told you what a penguin is, so let me pause and tell you what a penguin is, because this is a little bit off topic, so we'll just take a little bit of an interlude here. So QCD actually affected also not just the physics of strongly interacting particles, but also weak interactions. So weak interactions, unlike strong interactions, can change flavor. So I talked about the different flavors, bottom, top, up, down. To go between them, I need weak interactions. And so I can do that with particles like a W boson. It can change the flavor. But it turns out that QCD has an interplay with the weak interactions where it can cause, at low energies, things to look different because of the existence of the strong interactions. And one such thing is these what are called penguin diagrams. There's a famous bet involving John Ellis and Melissa Franklin, when Melissa Franklin was a student at CERN before she was a tenured professor at Harvard, which she is now. And they bet over a game of darts that John couldn't put the word penguin into his paper, his next paper, and he lost, so he had to put penguin in his paper, and that's where this name came from. So this Feynman diagram was drawn as a penguin in order to meet the deal. Anyway, so QCD can have impact on electroweak physics and the physics of transitions that we use to probe weak interactions. Okay, so that kind of takes care of the early 80s, and now let me turn to the sort of next period here in the diagram, kind of 83 or so, up to 2000, about 20 years ago. And this period is not sort of easily categorized in terms of individual events. It's more a lot of things were happening and fields were emerging where people were sort of grouping into groups that would work on particular topics. And so I'll tell you about some of those things, and I've sort of listed here 5 of them. There's actually more than 5, but these are sort of 5 important ones. One of them is this word that showed up in this earlier period called factorization. I'll tell you what that is. There's something called a Monte Carlo event generator. There's a nature of doing perturbative QCD, so doing expansions in the coupling, and that sort of became important, and it became its own field of study that people became experts in during this period. There's sort of the fact that data was really proving that QCD was the right theory, and that became precise during this period, and something called effective field theories, which is actually something that I work on, and I'll describe to you that as well. So we'll step through these one by one, starting with the first one. So what is this factorization? Well, if you looked at this collision that I showed you, you may have noticed that it looks pretty complex. So how the heck do you think you're going to be able to describe that? Right? It's a very complicated thing. So the basic idea is as follows. We can break it up into pieces. So if we want to calculate the probability of A given B, and we can have some kind of intermediate step C that we can identify that's useful, where it's easier to calculate probability of A given C and probability of C given B, then we can do the calculation of probability of A given B by summing over all C, or summing over the most relevant C, the most probable C. Even if we leave some terms out, that's okay. So that's the basic idea, is that we want to identify the most important C's, and we want to do calculations in sort of putting pieces together. And it turns out that the pieces of the puzzle are actually, the pieces of this collision can actually be treated to a large extent independently, and that's what allows us to make progress. So for a process like this one, we can break it up into a bunch of different pieces that are color-coded in my picture here, and do calculations of probabilities of certain things happening, or cross-sections, if you know what that is, based on putting those pieces together. So there's some probability of taking the particle out of the proton, and then there's some probability of that particle undergoing a particular hard collision, producing the Higgs boson. There's probabilities of certain types of jets being formed, which are both these green ones in the initial state and these blue ones in the final state, and then perhaps also some soft radiation playing a role. So that's the idea of a factorization, is that there exists a formula of this type, and that allows us to do calculations in pieces. And the nice thing about it is that those pieces are recyclable. So we can reuse them. We don't have to calculate them again and again. We maybe have to calculate some pieces new for a new process, but other pieces we can recycle. And that allows us to make a lot of headway. So different parts of the problem don't depend on other parts of the problem. This hard interaction doesn't really depend on what type of thing I measure about the jets. These jet-type functions don't depend on what type of hard interaction I actually was undergoing. The soft radiation only knows about very global properties of the jets. It doesn't know about the particulars inside the jet. And these initial state functions called parton distribution functions, they don't even know about really the collision. They're just providing some initial conditions for the collision. Now, I can make the problem simpler, and I can do that if I want to be agnostic about certain properties of the problem. So for example, if I don't care really that I'm producing here 3 jets and 2 leptons, if I allow other possibilities, and I sum over all of them, then I can use the well-known fact that if I sum over all possible outcomes, then I have to get 1. So the sum of the probabilities will add up to 1. And that allows me, for example, to simplify the formula down just to 2 parts, this initial state part and the hard interaction here, and get rid of the kind of final state part. And that is something that we do all the time to try to simplify these types of formulas that I'm talking about. And famously, the proofs of this type of formula, rigorous proofs, were done by Colin, Soper, and Sturman, including this 1988 paper of theirs, which is rather famous. What this formula does, this factorization, is also it separates the weak part of QCD from the strong part. So we're understanding sort of where the strong interactions are strong and where the strong interactions are weak. They're weak at short distances, which is this magenta blob, and that's this, what I call hard function here. And they're strong at long distances, and that's described in these distribution functions. So the separation of the scales, the weak part at higher energies and the strong part at lower energies, is done in these factorization theorems. If you want to think about kind of what's going on, like why do the pieces separate when I have these 2 different time scales involved, you can think of an analogy with a Bragg scattering. If you're doing a Bragg scattering with an X-ray, the X-rays probing a very quick snapshot. And if you're looking at the crystal, the atoms in the crystal which are moving around, they don't really have time to react and move. Their timescales over which they're moving is much longer. So you see that it really looks like a crystal where the atoms are frozen in. It's the same type of thing here, where we're doing this scattering at very high energy, and we're taking a snapshot of the proton when we're finding a particle with a certain momentum, which is this X variable in this formula. And this is kind of expanding out for you on what I had on the previous slide, where I had this symbol O times, that sort of say, put things together. Now it's being expanded out to tell you that actually it's probability densities, really, that we're talking about here, not just simple numbers. But it's not really more complicated than just having some integrals that you have to do. Okay, so that's what factorization is. It means these collisions that look very complicated can actually be simplified. Let me tell you what a Monte Carlo event generator is. So experimentally, when we want to make predictions, we still need to make predictions that kind of follow all the particles and that allow us to sort of, if we have a detector, to see how is the detector going to react to certain particles being put through it. And so we need to have ways of generating events. And that's what these Monte Carlo event generators do. And they combine together kind of two parts of the problem that I described to you: the production of the jets, the sprays of radiation, so that's what's called the shower, and that can be described with perturbative aspects of QCD, these DGLAP equations that I mentioned, and it puts those together in sort of a Markov chain type process together with some model of how the hadronization occurs, where the particles end up being bound together into the protons or other hadrons like pions in the final state. And together those properties, when put into some computer code that it can generate events and millions of events that you can then bin and study, is called a Monte Carlo event generator. And this is kind of its own field. It's gone through a kind of evolution from these early days that I'm talking about now, where this picture was the right picture, all the way to today, and it's still undergoing evolution. So I'll kind of jump forward to kind of today about what kind of all the ingredients that are inside these Monte Carlo showers, and it's sort of capturing a wide range of rich physics, both this hard collision that I've been talking about, secondary hard collisions, decays of particles in the final state, all sorts of things. So resonances, et cetera, even QED effects where we have some radiation from QED, not from the strong interactions. So this is a rich field, and it's ongoing. Let me turn to perturbative QCD. So the idea in perturbative QCD is that we can calculate these probabilities, and that at least when the coupling is small, that we can expand in it. And that's known as calculating a leading order, next leading order, next leading order, as I go different orders in the coupling. If you've taken a course where you've encountered perturbation theory, then you understand the basic idea here. But these calculations get harder and harder, and so you don't want to do them unless you have to. But it turns out that for various reasons, it's actually important to do these calculations because the precision of just the leading order term is often not enough. And the coefficient could be large even if the coupling is small, such that this next term is just as large as the first term, and that was a surprise, back in 1980s or late 70s, where certain process it was worked out that QCD, which is the star here, is actually what agrees with the data. So we really do know that we're talking about the right theory, and we can rule out other alternate hypotheses. Here's an advanced version of that. This is coming from Atlas. This is sort of modern day experiments and CMS. The CMS one is bigger, and the Atlas one's in front, and CMS has many more measurements. You can't really see them. I can't really even see them from here. The Atlas one has fewer measurements, and you can see, hopefully, that both the theory, which is these blocks, and the data, which are these colored things, they're all on top of each other, and so there's very good. The theory is kind of hard to see because experimentalists made this plot. You can see over here, the theory and the experiment don't quite agree. So there's some places where there's still mild disagreements, but a lot of this thing, we have over many, many orders of magnitude agreement between experiment and theory. Okay? And so this is sort of QCD is at the heart of those theory predictions, and we see that the calculations are working. And it's not just for kind of total cross-sections. These are showing you just total cross-sections for producing a W boson or top quarks, Higgs boson. There's lots of different ways of producing a Higgs boson. Those are sort of total probabilities of producing one of those particles, but also distributions, where we look at, as a function of some momentum variable. Maybe it's the momentum of a jet in the final state, and maybe that jet comes with different angles. These different symbols are different angular regions in the detector. That making predictions for those type of distributions also works very well. So QCD is working and agreeing with experiment. All right, finally, let me talk about effective field theory. So this is a method that people developed once they realized there's all these rich phenomena in QCD, and maybe just using the same tools to try to attack all of them is the wrong way of going about it. Maybe we should be making more specialized tools for each different type of phenomena and kind of even coming up with a new field theory or a new theory that we could derive from QCD to explore those phenomena. If the degrees of freedom, the relevant degrees of freedom, are different than the QCD degrees of freedom, if the degrees of freedom are protons and not quarks and gluons, then maybe we should be talking about a theory of protons and hadrons rather than a theory of quarks and gluons. That's sort of what's done in what's called the nuclear forces or chiral perturbation theory, where we use the symmetries of QCD to constrain another theory that has emergent degrees of freedom in it. There's other kind of limits of QCD. All of these different theories in magenta here are different effective field theories that are obtained from QCD by taking different limits and exploring different phenomena. I'm not even giving you a complete list, but I'm giving you sort of a set of important ones. So taking very high temperature gives you something called hard thermal loop effective theory. Taking high density gives you another effective theory. There's a limit that gives you a soft linear effective theory that Ignacio mentioned, which describes the theory of jets. There's theory for top quarks, etc. And lattice QCD also makes use of these methods, even though it's a non-perturbative method of dealing with QCD. The idea that you can make expansions is something that also lattice is exploiting all the time, so there's a lattice effective field theories as well. So I'll just give you a couple of examples of this. One of them is just this first one I mentioned to you, where instead of thinking about the quarks and gluons, you start thinking about the proton and the pion as your degrees of freedom. And you can derive a theory called the chiral Lagrangian that comes from QCD and the symmetry breaking patterns of QCD. You code those in an emergent field theory, and then you can do calculations with it. And people have pushed this to really high orders in the expansion that's involved in deriving this effective field theory, and made predictions for nuclear properties. Here, a two-nucleon state, which is a bound state called the deuteron, between a neutron and a proton bound together, and calculating some electromagnetic property, namely its quadrupole moment, and it gets very, very high precision, which agrees with experiment. QCD also has impact on weak interactions, as I mentioned. Here's one example to show you that the impact can be large. So this is what's called a flavor-changing neutral current, where a B quark changes into a strange quark. It turns out that can't happen in the standard model without having what's called a loop. And loops make things smaller. So this is a suppressed process for a B quark to change into a strange quark. In this picture here, you're emitting a photon, and there's like a loop, and it's got a top quark and a W boson in it. And it turns out that QCD changes the strength of this interaction by 50%. So if you just calculated this without having any additional QCD radiation, you'd get 0.2 for the strength of the interaction. And if you add QCD, it changes it to 0.3. And a 50% interaction change like that at the amplitude level, this is quantum mechanics, so everything's amplitude squared, 50% becomes more than a factor of 2 change in the rate for this process to happen because of QCD effects. And people, because they wanted to make sure that they really understood this is a process that's used to search for new physics, have pushed things to enormously high order and calculated crazy diagrams which describe the higher order calculations of these types of couplings. So far, things agree with the Standard Model. Otherwise, you would have heard about it. Another effective field theory you can look at is what's called heavy quark effective theory. This happens when you have a heavy quark bound to light degrees of freedom, or like a heavy quark, like a B quark, bound to a light quark, like a D bar. That makes what's called a meson, rather than a baryon, like the proton. And by thinking of the limit that heavy quark is heavy, you can make a lot of progress. Basically, it looks kind of like a hydrogen atom, where you've got something really heavy, and hydrogen, it's the proton sitting at the middle, and the electron's light flying around outside. And here it's the B quark that's heavy, and the light stuff is relativistic, not non-relativistic. The electron in hydrogen is non-relativistic. Here it's relativistic stuff, and it's strongly interacting, so it's really called sometimes brown muck, because you don't really even resolve exactly what it is. But you can use this limit and the symmetries that come about it from taking the B quark to be heavy. You get sort of enhanced symmetries of the theory. You can use those to make predictions, and that's been enormously successful, both in, originally for looking at things like flavor-changing couplings, something called VCB, as well, even today at our conference, we heard a talk by Zhuxuan Sun, my student, about heavy quark transverse momentum distributions. This is sort of telling you about the probability of a heavy quark to become one of these bound states, and then what kind of transverse momentum does it obtain? If it has no transverse momentum, and then it becomes this bound state through hadronization, it picks up some transverse momentum. What does that distribution look like? And there's very interesting, what are called sum rules that one can derive using the symmetries of this effective field theory. So I'll give you some examples from the workshop that are just student talks, just calling out a few students in some of my subsequent slides. This is the first one. So soft collinear effective theory. This is the theory of jets that I was one of the co-inventors of. And it's actually a very rich theory. I'll just give you a very brief snapshot of this theory and a couple of examples. But it's a very active field, and people have been working on it for sort of the past 20 years, coming up with more and more phenomena that they can describe with this effective field theory. And that's because it's the effective field theory of collider physics, basically. So if you want to see more than I'll talk about, I'm pointing you at a review article here. So how does this effective field theory work? Well, it takes the collisions that I introduced to you, and it makes use of this idea of scale separation. You identify that all the different parts of the problem have different scales associated to them, and then you set up expansions and ratios of those scales, and that all leads to this kind of factorization that I was telling you about. If we start treating the parts of the problem as independent, coming up with kind of independent field theories for the different parts of this collision, then we get this theory called soft collinear effective theory that tells how these things interact with each other at different scales. And kind of the systematization of this process, putting it out on a scale of energies and seeing what's the relevant scale for all the different degrees of freedom in this collision, that's what's called SCT. So it's been used to do various things. One example of what it's been used for was to obtain sort of 2 orders beyond what people were previously able to obtain in certain calculations for the production of jets and E plus E minus collisions, and then do fits to data to determine the strong coupling constant. So the strong coupling constant at some characteristic scale of the Z boson mass, which is 90 GeV, comes out to be some value, and simultaneously you're also fitting some hadronization, so you have enough control of the theory to understand sort of what the hadronization effects are and how they're described using these methods of effective field theory. Now, in the conference, this is sort of a field that, where these plots were produced over 10 years ago, but at the conference we also had a talk by Miguel, and this is an ongoing field where people are still looking at these type of fits and improving them. And with his updated analysis, he was able to achieve stability of these type of determinations of the coupling constant when the range of the fit that you're doing over the experimental data has changed, something that was hard to do in the past. There's also a very active field, and it was very relevant to the conference we had, called transverse momentum distributions, or TMDs. This is something that's very important in the US to the nuclear physics program, and it's sort of one of the key motivations for what's called the electron-ion collider, where in the 2030s we're going to be colliding electrons and ions together and exploring the physics of those ions as well as of the proton. So this is a generalization of what I've told you about with parton distributions, where not only one variable is relevant, but now you're actually accessing additional variables. You're not getting just a single snapshot in a single time slice of the proton, but you're getting three-dimensional distributions. So you could, if you like, you're along the collision axis. Previously we were getting a snapshot, now we're asking questions transverse to the collision axis, and that's the nature of the word transverse in the TMD. And at the conference, we saw a lot of talks about this. A lot of the conference has been about this, and I'm just calling out a couple. One was by Moose. I didn't find a picture of you. Sorry. I didn't have time to ask you for a picture. But he gave a nice talk. This is actually work with also with the local group, with Ignatius Skimimi and Alexei Vladimirov. And their group is actually one of the leading world groups around the world in the physics of transverse momentum distributions. So they are often leading the pack as far as studying the physics of these distributions. And so in this conference, we heard results at next and next and next and next, the leading log order, produced by their collaboration and fit to experimental data. And this is showing you sort of just one snapshot of their analysis. There's also been work beyond sort of the leading description, and that was something that also in this meeting, in particular in the session on Monday, we talked a lot about, and there was various talks about going beyond sort of the leading description, what happens at subleading order. You get access to new information, new quantum information about the proton, and it's kind of complicated, so I haven't gone into any of the details here. Okay, so now let's come kind of to, I've already given you some snapshots into the future, including some things from the workshop. Now I've tried to make a little bit of a more complete list of sort of some of the things that happened in this later period. So lattice QCD in particular around 2000 got very precise and started making precise predictions. I told you already about the parton showers and a little bit about what are called amplitudes. That's part of what's made higher order perturbative QCD calculations possible, is using some of those methods. Heavy ion physics I haven't talked about too much. I've talked a little bit about flavor physics, and I'll talk about a few of the items in this list just to cover this period. So let me talk about lattice QCD. So lattice QCD turned out, it took many years from its sort of initial proposal here to get things really precise. There's a lot of things you have to control in these advanced simulations, but things got better and better, and the methods and techniques of doing the numerical simulations got better and better. And nowadays, there are things that we can really rely on with kind of uncertainties that we can trust, which wasn't always the case in this intermediate period. So in this particular process, we're looking at a B meson, one of these heavy particles with a B quark and a light quark. In this case, a light strange quark, or S bar quark. And those two things can annihilate through weak interactions into a pair of muons, and this is something that's been measured. And here's a bunch of different measurements. Yet it's actually also you can calculate it. And the thing that you need to calculate is sort of the amplitude for these quarks to annihilate. And that process is sort of a single number that can be calculated in lattice QCD. And so that's what's done. And it's called F sub B. And actually, the lattice QCD calculations are so precise that they're like the smallest part of the error budget in this error bar making these predictions. So things have really advanced a long way. We can actually make real predictions and compare them to experiment. And you see the latest results from CMS here are in good agreement. And the theory is winning a little bit in terms of the uncertainties. So that's an example where the lattice is just making predictions, they agree with experiment. There's also using lattice to solve puzzles. There's a very old puzzle in what's called the muon anomalous magnetic moment. This is one of the quantities in nature that we've actually calculated, to 7, 8 digits of accuracy, and those calculations are phenomenal. But once you get down to the 7th and 8th digit, there's a little bit of disagreement between experiment and theory. And theory is like an enormous set of ingredients that have to be put together. There's sort of QED effects, electroweak effects, and strong interaction effects. And people, worried about the strong interaction effects, and some of those strong interaction effects are actually, again, extracted from data, but there's been this disagreement, which with the error bars that we're talking about, we're talking about these digits all agree, we look at the deviation, and there's some disagreement, it's like 5 sigma. And that's been around for many, many years. And the experiments have been improving, but not changing their number, and work has been done here as well. Lattice QCD has recently kind of got to the stage where the uncertainties have gotten small enough that they can start to have an impact. The first such calculation was done by what's called the BMW collaboration. The uncertainties here are still larger than these, but comparable. And the number that they were getting is actually falling in between. So that's sort of removing one of the methods of calculation here and replacing it by the lattice, which is sort of a better method overall because it's a non-perturbative simulation of QCD. And so we're very hopeful that this will at least make the standard model prediction definite in the future. Another thing that's happened in the past, say, 10 years is that we've found many, many different examples of hadrons. In particular, at the LHC-B experiment in the Large Hadron Collider, which is a dedicated experiment, they've observed an enormous number of unexpected states of hadronic matter. So if we look at the states of hadronic matter, we have a whole book full of those states, and these ones were, to a large extent, things that nobody thought would appear. They're kind of combinations of quarks that are often what are called exotic, so they might involve not just a quark pair, but like 4 quarks, or 5 quarks even, or some kind of molecule between the hadrons that's bound and has a lifetime that can be measured experimentally. And so there's a whole field that is interested in sort of making predictions for what's going on with all these states. Finally, let me mention jet substructure. So I talked a lot about the physics of a jet, the spray of the radiation. The LHC is such a good experiment that its energy resolution is so fine that we can ask questions about what's going on inside the jet. One way of thinking about doing that is kind of borrowing a picture from astrophysics and the CMB, where we look at correlation functions on the sky, and we can do the same thing, but now we ask the question about looking at correlations. So that's done for the CMB in astrophysics. This little picture in here actually comes from the CMB. But now we can do the same thing inside of a jet. We can ask for a 2-point correlation function, or a higher point correlation function, of the radiation pattern inside the jet. And so this is some correlation function with some angular separation between the detectors, and we ask about what does that 2-point correlation function say about the radiation. And it turns out to be a very interesting probe. This is a very exciting field, and people are making predictions and coming up with new ways of doing measurements based on these ideas. And in this picture here, I'm showing you this 2-point correlator that was measured by Elise, an experiment at the LHC. And it's shown for different angles here on the x-axis. And you see actually a transition between perturbative behavior of QCD, where this kind of shower is the relevant way of thinking about it, over to a picture of hadronic matter, where you're just having free hadrons, and and you're sort of probing and putting your detector on those hadrons. And you're seeing this kind of transition in the data between those two extremes. You're seeing the confinement kind of appear right in the middle of this picture. If you just took free hadrons, you get the pink curve. If you take perturbative QCD, you get the yellow curve. And we'd like to understand this transition better. But this is giving you kind of new access and new method to probe these type of questions. Okay, so I promised I'd end with 10 open problems, so let me do that. I have no idea how long I've taken because of the pause in the middle, but here's the 10 open problems that I came up with. So one of them would win you $1 million. So feel free to try. And that is the following. Give a mathematical proof that Yang mills, namely QCD, has a mass gap, namely that a theory of massless gluons produces hadrons with finite mass. Sounds plausible, but it's a very tough problem. Part of what makes this a very tough problem is the phrasing of the problem, that you need to, how rigorous does your proof have to be? It has to be fairly rigorous in a mathematical sense. And that's what makes this $1 million target very hard to get to. And you're asking here for kind of a mathematical proof. Numerically, doing these simulations, we do have evidence that this is the case. Like we're very strongly understand that this is the case. We just don't understand sort of exactly what in those simulations is leading this to happen at an analytic level. And so this is just showing you sort of getting massive hadrons out of QCD by solving this path integral on the lattice. But that's not enough to get you the $1 million. And if we did make progress on this problem, which is probably the hardest problem in QCD, then I think it would actually help us with other questions that we want to ask and answer. But it's probably, the hardest thing to work on, and I actually don't recommend spending time on it. What are some other questions? So one of them is about this transition to hadronization that I described to you from the point of view of these showers, where we had the shower, the spray of radiation, and then the hadrons were forming in the final state. And I told you that we're built models to do that. And there's kind of very accurate models. They're able to predict the data. Sometimes they don't work. Most of the time they do work. But we're still doing modeling here. We're not using QCD itself to figure out how a very energetic quark becomes eventually a bunch of hadrons. We're attaching a model to our perturbative QCD predictions. Could we do better? It turns out this is a question you can't answer on the lattice. Nobody knows how. So you don't have any method of doing it, and so that's why I made it a challenge to find a better method. What we currently do is sort of a mixture of theory, simulation, and experiment to constrain the models, but you'd like to do better based on first principles, and that's an open problem. I mentioned to you this factorization formula, and the way I described to you is sort of like inevitable. But it turns out that actually proving these types of formulas is difficult, and we actually don't have a lot of proofs from first principles about when things factorize. We know it for a lot of different cases, and we see it working, but exactly where is the dividing line, and what are the characteristics that define the dividing line between things that factorize and things that don't factorize, processes that cannot be described by the formulas like the one I presented to you, we actually don't know where this is. So maybe it's there, maybe it's over here in this abstract space. We don't know where it is. We know some examples on this side. We know some examples that can be proven on this side. We have many more examples where things work because we agree with experiment. But we don't have a rigorous theory of this. And so this is something that's a challenge that should be met. And maybe the picture is even more complicated than that one. Maybe there's some kind of intermediate regime where the factorization is violated, but in a small, controllable way. We'd like to map out how factorization works in more detail than we understand today. So that's number 3. Number 4 is about this transition between the quarks and gluons to the protons to nuclei. And I described it to you, but can we control all stages of that? And the answer is not really. And if we could, then we'd be able to make predictions for kind of the stability of nuclei as from QCD rather than from modeling. We'd be able to explore things kind of away from stability that still exist in, say, astrophysics environments. And that would be powerful. We'd be able to make impacts on nuclear astrophysics if we could control this whole chain. We could also make impacts on testing fundamental symmetries. So there's experiments that look for things called neutrino doubleless beta decay. It's like a beta decay that can only happen if the neutrino is what's called a Majorana particle. And sort of those type of experimental measurements depend on some properties of the nuclei that they use in those experiments that you'd really like to have a better theoretical control over. And if we understood this chain better, then we could. Here's number 5. So in a heavy ion collision, which I haven't mentioned too much, it turns out that we produce liberated quarks and gluons, and they do sort of collectively flow. So they behave like a fluid. And it turns out that they behave like almost a perfect fluid. They behave like a fluid with very small viscosity. Okay? Viscosity is like friction in fluid mechanics, and in these heavy ion collisions, the viscosity to entropy to get a dimensionless number has been measured, and it turns out that it has a smaller value. This is viscosity over entropy on the y-axis here, has a smaller value in these quark-gluon plasmas than it does in many common things like water. Okay, so sort of the fluid that we know in nature that exists with the sort of smallest value of this viscosity. And so that's kind of interesting, but we don't really understand all the details. We can model again, but we'd like to understand better and what's going on here. Another question that's sort of related to the phases of QCD and kind of thinking about things at finite temperature and finite chemical potential, i.e. finite density, is mapping out a phase diagram. So we're familiar with the phase diagram of water. We've got liquid, solid, gas. This is the analog for QCD. And there's different phases. I've talked about some of them. At very high temperature, we liberate quarks and gluons into the plasma. Down here, we have hadrons. Maybe over here, we have something else. We'd like to map out this in more detail, in particular, understand if the transition between quark-gluon plasma changes at some critical point. From over here, where it's predicted to be first order, to some crossover, is finding this critical point is a goal. And that's both an experimental goal as well as a theoretical goal. Number 7 is solving the lattice QCD finite density problem. You might think I could do something on the previous slide using lattice, but I can't because the action becomes complex, and then I no longer can do this importance sampling. I have complex weights, and the problem is then unsolvable, and people have tried for many years to solve this problem, but it's a very hard problem, and if you could make progress, you'd also have an impact on condensed matter physics. There's related things that are related to finite time, which lattice also can't do, and that's also related to why lattice can't really do help with this real-time hadronization problem. And there's been some recent progress in that direction. Number 8 is about neutron stars. So neutron stars are a state of QCD matter, and it turns out that the equation of state for a neutron star matter is actually having an impact on astrophysics, in particular on the in-spiral of neutron stars, where we observe gravitational waves. And so it affects these things that I've put in this list, including this tidal deformability, which is something that affects measurements made at LIGO and other gravitational wave experiments. And we don't really understand exactly how the equation of state looks. We can actually constrain it from the data, but first principle calculations can be kind of made on the ends of the plot at high energy densities and low energy densities, and it's hard to make predictions in sort of the relevant middle region. And so figuring out the exact equation of state from first principles is an open problem. Perturbative QCD and what is the sort of ultimate method? There's been a lot of advances, but there's sort of still this method, that method. Can these things come together? Is there sort of a coherence to this? I want to conclude shortly, so I won't go through all of this, but I've already kind of mentioned this, and that's a challenge for the future. And it's an important one because these higher order calculations are really important in many cases for getting agreement with data and for making predictions that are relevant for testing other parts of the Standard Model, such as the fact that Higgs couples proportional to its mass. Number 10 that I left up is just determining the strong coupling itself, which is coming into all these predictions. We know it pretty accurately, but it turns out that using different methods, there is some variety, and in particular, these ones I showed you with the jets don't tend to agree with the lattice, and that's kind of a challenge that we're still trying to understand. And so that I put also as a challenge for the future. Okay, so let me conclude. I say after 50 years of studying QCD, we've learned a lot. We have a lot of control over it in a lot of different regimes, but there's still some mysteries to solve, and I just presented you 10, and I've summarized them. Some of them are here again with these pictures. Thanks.
So, questions? Please raise your hand so I can bring you the mic. No questions? Okay, sorry.
In the open problem set, you had two kinds of 7. Are they somewhat related?
Yeah, they are somewhat related. Thanks for asking. Let me go back. So both of these are related to the fact that lattice QCD is a Euclidean method. So it's not solving problems in Minkowski space where time is treated different than space, but it's doing a kind of transformation of time to make it into another spatial variable. And that's okay for many static problems, and lattice is therefore very good at those static problems. But if it's a real-time problem where there's some evolution in time and then something's happening in space, where the Minkowski nature of the problem is actually important, then lattice can struggle. Sometimes there's methods of getting around it, but that's kind of what the limits of lattice are. It's sort of really because it's doing this Euclidean path integral. It's specialized to Euclidean problems that I can phrase in a Euclidean way. And both of these things are actually related to things where an I shows up and it becomes Minkowski. And so instead of having an action here which is real, this term here, it turns out to generate a complex phase, and that's sort of analogous to having Minkowski space matter. And that's the sense in which these two are related. They're both related to sort of having complex valued integrals to do instead of being able to just get away with real integrals.
Okay, thanks.
More questions?
Could you explain why lattice QCD cannot help understanding better the hadronization problem?
Yeah, so it's basically because of the fact that to do that, you're really talking about some process that's happening in real time, and you cannot make it, no one knows how to make it Euclidean. So, since you know too much, I could try to get technical, but I'll say something technical, maybe I'll try to make it simpler, but for a part-time distribution function, if you take moments of that problem, integrals over the x variable with any power, weighted by any power, x to the n, it turns out to Euclideanize the problem. And so you can make the part-time distribution function, if you study its moments, those are questions that you can answer and ask on the lattice using Euclidean methods without having complex phases. But the analogous thing doesn't work for real-time hadronization or fragmentation functions. You try the same thing for a fragmentation function, you just don't get something that it can be Euclideanized on the lattice. It has to do with the fact that in the fragmentation process, you're producing a hadron plus anything else, and it's in the final state rather than sort of in the initial state, and because of that, you're not able to sort of do the complete sum over states in the same way, and you can't make it a Euclidean problem. So it's, again, it's this I and the Minkowski nature of the problem. It's, I think, a very worthwhile thing to think about, that particular problem of how do I make something like a fragmentation function, which is an analog of this F function I was talking about, but that's the final state analog. How do you make that into something that the lattice could deal with, just at a theoretical level, is a very worthwhile problem, because if you could do that, it would start an industry in that field.
In the spirit of this being an overview talk, I just wanted to make a general question on the last part.
Yeah.
Out of these 10 problems, which one for you is the closest to being solved in the next future, and which one is the most pressing? Which one will produce the biggest breakthrough in QCD?
This one that's on this slide would certainly produce a big breakthrough if you could solve it. And I don't know if I could really say that one is more important than another, because each of these problems is important to a field of physicists that works in that area. And they've decided that, you know, the physics surrounding that problem, maybe not just that problem itself, is the most important physics. So I can't take sides. But, you know, I certainly care about the one that's on the screen here. And, you know, I'm number 2 or number 3, this problem I'm actively thinking about. So.
Okay, I think we are a bit late, so thank you very much for your nice talk, and I'll see you in the next colloquium.